Good evening.
What's going on? Okay, so after last week, we dealt with the infinite potential well, talked about a particle trapped inside a potential well. Did your homework on that as well. Today we're going to do the absolute opposite. We're going to talk about what happens when a free particle hits some barrier. What will happen to it? Will it be reflected? Will it be transmitted? I'll define the expressions as well. So first, I'm going to give a short intro. I'm going to talk about a potential barrier. Potential barrier is this thing. This is what you talked about in the lecture as well. And I'll go over the main steps that you have to go through when solving such a problem. I'll define the problem. We'll talk about probability currents and how to calculate different coefficients. And then we'll solve two examples. One will be the step potential barrier. So there's just one change in the potential. And then a little bit more subtle example will be the delta barrier, which also has some interesting features. So let's get right into it. We'll start off with the potential barrier. Let's talk about the setup of the problem. And how to solve it. So we're talking about a potential V of x, which changes abruptly in space. It is some V naught, some constant value between 0 and L, and 0 everywhere else. So this V of x is the x-axis. Now we're going to consider a particle that starts at minus infinity and it has a definite momentum k or h bar k in the plus x direction. So the particle starts off all the way over there and it has a positive momentum in this direction. Now because all the way over there is no potential, v equals 0, this is like a free particle. So if we know that it has a definite momentum h bar k, we know the energy. Is the energy of a free particle h bar k squared over 2m. Because the potential that is changed here, all the way over there, it doesn't affect. It doesn't affect the particle. So this is the energy. Now the particle travels, it hits the point x equals 0. Particle gets to. And now the question is what will happen. So if this were classical mechanics, what happens? That's the question we want to ask, and that's the question we want to deal with today. So if this were classical mechanics, then what would happen? Then we'd have to differentiate in two cases. Either E is larger than V naught, so the energy is higher than the barrier, in which case the particle will pass, 100%. There's no probability, there's no doubt, so particle passes. And if the energy is smaller than V0, the particle is reflected. There's no doubt. This is classical mechanics. I hope this is clear to everyone, right? This is obvious. Now, quantum quantum mechanics, obviously it's all different. Quantum mechanics, there is a possibility that a particle with high energy is reflected, or it may pass. There's some probability for anything to happen. And the same thing for an energy which is lower than V0. The particle could be reflected, but it could also pass through. This is called tunneling. Because it builds a tunnel through the potential, goes through, so it's called tunneling. So in quantum mechanics, no matter what E is, there is a probability for both. Either it passes or it goes back, no matter what the energy is. Of course, the probabilities will depend on the energy, but there is always a certain probability to pass, certain probability to go back. If you send out one particle starting off at all the way over there at minus infinity, coming at the potential, a priori, you have no idea what's going to happen. There's only a certain probability of something happening. If you send out 1,000,000 particles, then you can say which percentage of particles will fly back, will be reflected, and which percentage of particles will go past and go to plus infinity. So obviously the probability depends on the energy, and the objective of scattering theory, and our objective today, is to determine these probabilities. For reflection and transmission. Okay, questions so far? Now, of course, this is not surprising, the fact that it's probabilistic. Quantum mechanics is a probabilistic theory, so it's not surprising that, that whether it's reflected or transmitted is probabilistic. In fact, it is actually wrong to talk about a particle starting at minus infinity with a definite momentum. This is something that we can't even say in quantum mechanics, because if it has a definite momentum, then how can we say it starts over there? We don't know where it is. It's the uncertainty principle. If we know the momentum, we don't know where it is. So the situation that I've been describing is actually wrong. Okay, although we use it for our intuition, it's actually a wrong description. The right way to think about it is in terms of a probability current. We think of the problem in terms of probability current. Let me define what that means. We know that there's a probability of finding a particle somewhere in space. So at the beginning, the probability of finding the particle is high all the way over there and low in this region where the potential barrier is. But it's high over there. Now, as the particle is moving in this direction towards the potential, the probability is moving like a current, like an electrical current. It's not electric, it's a probability, and that's why it's called a probability current. So we're thinking of this probability current coming from minus infinity and advancing towards the potential barrier. The probability current is given. This is a formula which you will prove in your homework. If you know the wave function of the particle, to find the probability, you need to take the imaginary part, and just the imaginary part, of psi star times the derivative of psi. Multiply this by some constant, h bar divided by the mass of the particle. And since the wave function is technically this could be a function of space and time, but we will limit ourselves to time independent case today. Nothing can be time dependent. The scattering parameters, whether it passes or not, is not time dependent because the potential is not changing in time. So we're just going to concentrate on the spatial part of the wave function. So if you know the wave function as a function of space, you can find the current as a function of space. We will see that in case for the regular scattering problems, it's actually independent of space. So not true in general, but for today, it will be space independent. We'll see this in a second. Just want to point it out now already. So in our case, J will just be a number with some units, right? Units of probability current. During the homework, you'll be able to think about what the units are exactly. And this is it. So the way we should think about this problem is that there is some incoming current, an incident current, Ji. When it hits the potential barrier, there is some reflected current, which we'll call Jr, as in reflected, and some current which passed the barrier, which we call Jt, transmitted. So we have down the words, this is incident, reflected, transmitted. Now it's kind of obvious the way we defined our what we call the coefficients. So the coefficient to be reflected, capital R, is just Jr over Ji, absolute value. And the transmission coefficient is Jt over Ji. So which part, right, this is a fraction, which part of all incident particles is reflected? That's the reflection coefficient. And which part of all the transmitted current with respect to the ratio with the incident current, that's the transmission coefficient. So when I say that the objective is to determine probabilities, what I mean the objective is to find R and T. That will be the objective for today for different problems, and you'll see that 80% of your homework will be finding these coefficients, and the other 20% will be analyzing the result. So this is what it's all about. We want to find R and T.
It's like in waves?
It's exactly like in waves.
So they have an impedance?
You can define an impedance. You can define an impedance, but we're going to... You can find impedance, it's going to depend on the value of V naught. But it's exactly the same. You could think of... The impedance has to do with the epsilon, right? With the dielectric constant of the material, right? It's 1 over the dielectric constant. You will see that if you compare it, I think the V naught is either, I think it's exactly equivalent to the dielectric constant, or up to some constant, but it's exactly the same idea. So if you understand it, because this is wave theory, right? It's a wave function. So it's exactly the same thing.
So in other words, it moves from, I don't know what we say Tavach in English, but
medium.
Medium?
Yeah.
So it moves from medium to medium.
Yeah, this is like, if you think of this as light, then this could be glass in the middle, this could be air on the outside. And then some is reflected, some goes past. In the case for glass and light, it's 4% going back and 96% going through. Fun fact. Same idea. It's the same physics. So if you know wave theory, if you understand how that works, it's the same physics going on here. You can get the same results. Good point. Okay, so if we know the coefficients, R and T, obviously we must have that the sum equals 1. Because the particle is either reflected or transmitted, cannot disappear. So the sum equals 1. Another way of seeing this is thinking in terms of currents, think of in terms of electrical currents. This is like a node. There's a current coming in and currents going out. So the incoming currents must equal the outgoing currents. People who have done circuit analysis know this very well. Incoming current equals outgoing current. So you must have that Ji equals Jr plus Jt. That's just by observing what's going on. If you now divide this by Ji, you'll get this relation. Right, and you get 1 equals Jr divided by Ji plus Jt divided by Ji. And that's just this relation. So it all makes sense. Yay. Okay, so now we know how the problem is set up. We know how to think about it, think about currents, what about particles. And we know that after we found the currents, we'll be able to find the coefficients. The only problem is, how do we find the current? In order to know the current, we have to know the wave function. So if we know the wave function, look how simple this is. All we have to do is find the wave function. As soon as we know the wave function, it's just a machine. Plug the wave function into the current, and plug the current into the formula for the coefficients, and you're done. So how do we find the wave function? We learned that a while ago. We solved Schrödinger equation. The time-independent Schrödinger equation is all we'll be needing today. And we already said that we know the energy of the particle because we know it has definite momentum k. That's an initial condition. So we know that it has a different momentum k. We know that it has a definite energy, h power k squared over 2m. So all we have to do to find the wave function is solve the time-independent Schrödinger equation. So all we have to do solve the Schrödinger equation. And how do we do this? We split up space. What do I mean by this? Notice that the potential changes abruptly in space. So it's 0, then suddenly it becomes V0, and then it becomes 0 again. It's very abrupt change, which is why we want to solve Schrödinger equation 3 times. We want to solve it in the area where x is smaller than 0, in the area between 0 and L, where there's the higher potential, and then again at x larger than L. And the Schrödinger equation looks different in each place. At x when x is smaller than 0, and I'll write this in momentum space, in position space, I'm sorry. There's a momentum? Position, I'm sorry. I'm running in position space because I want to know psi of x. So I'm interested in it. So in position space, at x more than 0, the potential is 0, so it's just the kinetic term equals the total energy. Remember, E is given. We know what E is. It's given in the question. In the area in between, there's a potential. And in the area where x is larger than L, it's the same equation like where x is smaller than 0, I have given these wave functions different names. I call them psi1, psi2, and psi3 in the different regions. So if this is our potential barrier, and here's x equals 0, here's x equals L, I have called this region 1, this region 2, and this region 3. Remember to always do this. This is how you start the problem. This is how you start solving a problem. Now let's rearrange the equations. After rearranging, we can write psi1 double prime means second derivative, equals 2me. What happened to my minus sign? No idea. Divided by h power squared psi1 of x. And here we get psi2 double prime of x. So all I've done is rearrange the equations. I will now define k squared to be equal to 2me divided by h power squared, and I'll define q squared divided, which should be this thing here, 2me minus v0 divided by h power squared. So I get three simple equations. So the equations look exactly the same. The only difference is there's a k here, there's a q here. Now because the energy is given, mass obviously is given, V naught obviously is given, we know what k and q are. We can consider them as numbers or quantities, not numbers because they have units, but as quantities that we know, because they're just a bunch of other things that we know. Okay, let's solve the equations. Questions so far? Oh. Wasn't the right one. So the solution, well actually this depends now whether we're considering E larger or E smaller than V0. We'll have to consider the two cases individually. And we'll start with the case where E is larger than V0. Because when E is larger than V0, then your Q squared is larger than 0. Right? If E is greater than V0, then Q squared is a positive number, a real positive number. K obviously is, that's always a positive number, but in this case, Q squared is a positive number. In which case, all of these differential equations are equivalent. They have the same solution, and they're oscillatory. So psi of x equals psi1 of x, which is some a e to the I kx plus p e to the minus I kx for x smaller than 0. Psi2 is c e to the I qx, that's the only difference, plus d e to the minus iqx, and psi3 f e to the I kx plus g I to the minus I kx. The very important thing here is, and this is where you have to be very careful, although the equations are exactly the same, or let's say the third equation, first equation are exactly the same, they both have k inside, you have to use different integration constants. They're obviously different because they're actually different equations. They look the same, but they're in different regions. So you must use different integration constants. That's a common mistake, so watch out for it. Before we continue, I want to give an interpretation of, you see here there's 6 different terms to this wave function. I want to give an interpretation to every single one of them. And the interpretation lies in the sign of the k, where there's a plus or a minus sign. So the first term, the k is positive, right? It goes to plus ikx direction. So this is the wave coming from, it's the wave or the current, what you want to call it, let's call it a wave, coming from minus infinity and traveling towards x equals 0. It's only defined in the region x smaller than 0. This is the wave traveling towards x equals 0. That's the initial wave. So if you think about it like this, right, this is our potential. So this is a e to the ikx. Now, as it hits this barrier at x equals 0, there are 2 options. Either the probability current is reflected, or the current, some of the current is reflected and some of it is transmitted. So the term b e to the minus ikx is still in the region where x is smaller than 0, so in this region, but it has minus k. So this is the reflected wave. The next term, c e to the plus iqx, is the transmitted. So it's inside the potential here. It could be above. I don't care about the energy at the moment. Doesn't matter whether it's above or below. This term will always be the. In this case, it must be above because the I. This is c e to the iqx. And now this wave continues to travel. Since with the wave, it travels towards x equals L. It is not defined beyond x equals L. So it's only this part inside the barrier or above the barrier. The reflected wave, by the way, goes back to x equals minus infinity. So it's reflected. Now the traveled wave, the wave that travels inside here, again hits a change in potential. And again, at this change, some of this is reflected. That's this term here. So this is the reflected.
That can actually happen, that he will come back, because here he's going to the potential, to the lowest, the D. He's going to the, he could, but it's not a wall like.
Quantum mechanics. That's what I said in the beginning.
No, I understood it. Okay.
Absolutely. Absolutely. I can even add on to this, and you will solve this problem in your homework. If you have potential like this, which is 0 on the outside and minus V0 here, and you have a wave coming from here, there's a probability that this wave will be transmitted, will be reflected back. You'll actually solve it and you'll find the probability that this can happen in your homework. So absolutely, yes. So this part, the e to the minus iqx, is the reflected part of C. So of whatever I managed to pass here can again be reflected back. And now the next 2 parts are simple. The f e to the ikx, obviously it's the reflected, it's the transmitted part of C. And the last part, that's the most interesting. Let's put these transistors, one coming back here, that's the d e to the minus iqx. And then here is the one which is transmitted, that's f e to the plus ikx. Now, after, say, a certain percentage is transmitted, now it will continue to travel until plus infinity. There is no chance of it being reflected back again. Excuse me?
There is no such a potential. We will also get the B E square minus IKX. Yes, this one. If we don't have such a potential, we will still have this one. Just to solve the question, solve the equation 1. The first in the equation in first region. There is no such a potential. But I mean, before the event happened, we don't have this potential. We will still have this one. So what's the difference between the? How can we understand the B E exponent as a refractory wave?
Because of minus k.
But if we don't have such a potential, we are also.
Well, so you agree that this is a solution of the differential equation?
Yeah, the solution is not related to the.
Right, so now you think about physics, you're trying to impose initial conditions. Right, and you're saying the initial condition is a particle traveling in the plus direction. So how come there is a particle with a minus direction? Is that a question?
Yeah.
So the answer is because there's a potential which is reflecting it.
If there is no such a potential, we can.
Let me just continue 1 minute, and I think I might answer your question here. Right? Because here, and tell me if this answers your question, it's for everybody, by the way, what I'm saying now, not just for the question. This part is transmitted. After it's transmitted, there's no more change in potential. So there's no way that this wave is reflected back. So from here we infer that G must be equal to 0. So wave cannot be reflected anymore. Hence, G equals 0. So here I've used the initial conditions, right? The fact that the particle started all the way over there, to understand that once it's passed, it's passed. Does that answer your question? No. If you're saying if the potential did not exist, so if space will just be like this, V equals 0 everywhere. And I'm telling you, initial condition is that the particle starts all the way over there, at minus infinity. Here, this is minus infinity. Okay? Yeah. The particle starting. I'm telling you, this particle has a momentum k. Yes. So the solution of this differential equation will be this function. Yeah. But then the initial conditions will tell you b equals 0. Okay. But this is not the problem we're solving. We're solving this problem. Okay. So with this problem, you can go back again. Yeah? Okay, any more questions? This is physics, not mathematics. This is important to understand. Okay, every part of the wave function has a meaning, and if we understand the meaning, we can automatically throw out some of the wave function. We know it's not true, this cannot exist. Excuse me?
Isn't it right to add that V is also has some component of the D wave that managed to pass?
That's absolutely correct. What you're saying is that after you're saying we're starting here, let's say by chance it went past, then it was reflected, and now it can be transmitted back again here, right? Or it can go back and forth from here 1,000,000 times to then pass. That is correct. And of course, if you look at the function of time, that can happen. But this, of course, is included in B. Right? All of this going in and then back and then out again is included in B. I don't know what exactly you did in the waves class or optics class, but if you spoke about interferometer called for Perron? No? Well, it's exactly the same thing. So when you get to optics and you do a Fabry Perot, it's exactly what you're saying. You can think of this as a light wave, and there's a mirror here, or some material, not a mirror, but like an 80% mirror, say, so 80%, for instance, go back, 20% come through, another one here, it's exactly the same thing will happen. Some of it goes past, some of it goes back. And of course, you can go back and forth, it's a cavity, and then go out. But of course, all of these things are included in A, in B, and so on. It'll automatically be included. But it's a correct observation. More questions? I look so shocked.
I'm trying to think about it as probability, because the particle is either bouncing back or tunneling.
Or the superposition. It's quantum mechanics, it's superposition. Until you measure it, you have no idea what's going on. That's what I'm saying. A single particle, a priori, you don't know what's going to happen. If you actually want to do an experiment and compare it to your theory, you gotta send out a million, 10 millions, 100 millions of particles, right? That's what Rutherford did, for instance, in his deflection experiment. You send out millions of particles, and then you measure out of the million, 500,000 went back, 500,000 came through. Okay, so the probability for one particle is 50-50. But a priori, what one particle will do, whether it'll go through or back, I don't know. Okay, so we have found our wave function, right? We've understood what it means. We've understood that this goes away. This is 0. So we can now find our currents. So here, this is what we're at. So the incoming current, I already told you, that's this part. That's what will be associated with Ji. This part here is going to be associated with the reflected current, and this thing here is the transmitted current. This thing here is just an intermediate state, and I'm interested in what will eventually go back to minus infinity and what will eventually get to plus infinity. So this barrier is an intermediate place. I'm going to have to use it for calculating, but in the end effect, I'm interested in these three currents. In this case, we now just get reflected current, as I said, is JR over Ji. We need to calculate them first, sorry. So let's calculate Ji. I'm getting ahead of myself. So by definition, that's h bar m times the imaginary part of psi star, that's a star e to the minus ikx, times the derivative of psi, a to the ikx. Going into the formula, the derivative here is ik e to the ikx. Now the e to the ikx cancels with e to the minus ikx. So the imaginary part, there's an I here, so this whole thing is the imaginary part. So we get h bar k divided by m times a squared. Okay? Clear? I'll do the same thing with the reflected current. So you see it's exactly the same formula, but with B. And the transmitted current, I'll use this one here. And I get h bar k divided by m f squared. Now, it's simple. The reflection coefficient is the reflected current divided by the incident current. So that's b over a squared. And t the transmission coefficient is f over a squared. So all we have to do is find A, B, and F. So this was the case where the energy is larger. The energy is larger than V naught. Before we actually go on to solve the example, I just want to say a few words about the case where E is smaller than V0. If we look back at our three equations, the three Schrodinger equations, I'll just remind you what the difference is. So first of all, regions 1 and 3 are unchanged. Right, I'll remind you of the regions. So here and here there's no difference. K squared, right? So K squared is still 2me over h bar 0. But remember that Q squared, the way we defined Q squared, it was 2m e minus v naught divided by h bar squared. Now since E is smaller than V0, this is a negative number, which means that Q, not Q squared, but Q, the square root, will be imaginary. So let's define G squared equals minus Q squared. So that's 2m v naught minus E divided by h bar squared, okay, for the order. Now G will be a real number, because this is positive. But now what happens? Schrodinger equation in region 2 is now, right, I plug in G squared equals minus Q squared. If you look back at what we had there, we'll get psi 2 double prime of x equals G squared psi 2 of x. So there's no minus sign. And the solution to this equation inside the barrier is that a psi 2 of x, psi 2 of x is some c e to the gx plus d e to the minus gx. It's now either an exponentially growing or decaying function. And as I said, regions 1 or 2 are unchanged. So they are still e to the I kx plus b e to the minus I kx, and psi 3 is f e to the I kx, no g for the same reason. So the difference is here, right? Compare this and this. The difference is in psi 2, where instead of an oscillatory solution, we have a decaying or growing function. There's no need to be worried about divergences, because this is only true if x is inside some interval. So now this is actually going to diverge. X is never equal to plus infinity in this case, or to minus infinity, because that's not the correct region, right? This is only true for x between 0 and L. So there's no divergences or anything like that, so don't be worried. But it's not oscillatory. That's the main point. But if you notice, the incident, right? The incident current, reflected current, and the transmitted current will be exactly the same, because from this we'll get Ji, from this we'll get Jr, and from this we'll get Jt. So the actual formulas will be the same. Same formula for R and T. But of course, these A's and A, B, and F, which enter the formula, they will of course be different. They will depend on G rather than on Q, so the actual solution will look different, but this formula is still correct. Question about this? All right, making progress. Okay, so let's solve the example of a stepped potential barrier. Excuse me? You haven't solved to the end. I told you that if you find the coefficients, then you found this. I haven't told you yet how to solve the coefficients. I will show you exactly how to solve that in the example of the step potential barrier. And then when you go back home, you'll do it for this. You'll take off at this point. And you were supposed to do it in the lecture, this example. Maybe you fell asleep. I don't blame you. Just saying maybe it happened. You did in class, right? Or is that wrong? Yes. You did it. And if not, you'll do it at home, so you'll do it at least once in your life. I'm sure you'll do just fine. So it's a step function, a theta function, Heaviside function, call it what you want. The question is find R and T for E larger than V0. This is V0 here. Of course, same initial conditions that we talked about. Initial conditions are always the same. The particle starts way over there, somewhere in Givat Shmuel, I think, and comes this way. Right? So it's the same initial conditions in all of our problems, and we're interested in how many particles will eventually end up back over there, and how many particles will pass this this barrier and end up all the way over there. Okay? Now the classical solution is obvious, right? We're looking at E larger than V0. So in the classical solution is just, yes, everything passes. So R equals 0, T equals 1. Hope that's clear. As we just learned, what we have to do now is solve the Schrodinger equation in two different regions, 1 and 2. So in the first region, remember we're at E larger than V0, so E is somewhere over here. So we'll get A e to the ikx plus B e to the minus ikx, and then we'll get C e to the iqx, where k squared is 2me over h plus squared, and q squared is 2m e minus v0 over h plus squared. I'm not going to go over the entire equation solving again, because it's exactly the same thing as before. The only difference is that we end after the second region, and obviously after we transmit it at x equals 0, we can't go back anymore, which is why there's no d here. So there's an incoming, a reflected, and a transmitted. That's it. We can now find our currents. So in order to find so let's calculate our currents. The Ji is going to be the same as before, h bar k over m a squared. The J reflected will be h bar k over m b squared. The J transmitted, and here you have to watch out, the derivative inside the imaginary part will now take down IQ. An IK and IQ. So the J transmitted will be h bar q divided by m c squared. Is this clear? This is fundamentally different than the previous problem. And I'll show you why it's fundamentally different. Because if you now take a look at R, the reflection coefficient, that will be the same as before. If you divide this by this, all of this prefactor just cancels. But if you look at the transmission coefficient, so I'm dividing this Jt divided by Ji, the h bar cancels, the mass cancels, but the q does not, the k does not. So we get here q divided by k times c divided by a squared. This is fundamentally different than what we did here. It is important, I've shown to you here by example, that it is important to go through all these steps, calculate your currents, because otherwise you get the wrong formulas here. And then you won't get R plus T equals 1, and you're going to get really bugged out because it's going to make no sense. And we're looking for physical intuition. So it's important to always calculate your probability currents before you go on. Okay, questions about this? So what I have shown to you now, right? We went through the steps we already did for the potential barrier. We have found a general formula for R and T for this question. What we have to do now is find the coefficients A, B, and C. How do we find these coefficients? How do we find these coefficients? Boundary conditions, very good. So we need to now impose boundary conditions. And we have two boundary conditions. One, continuity of a wave function. The wave function must be continuous. And the second boundary condition is the continuity of the derivative. Of the wave function. So both psi and psi prime are continuous. It is obvious I didn't write down those. X smaller than 0, x larger than 0. They have to be continuous, of course, at x equals 0, right? That's what I mean. So, continuity means that I plug in x equals 0 here, and set it equal to x equals 0 here. So from psi of x equals 0 plus, so the positive side equals psi of, let's do minus here. Minus, doesn't matter though. I get a plus b equals c. And from the derivative, psi prime at 0 minus equals psi prime 0 plus, take the derivative, so we'll get the equation ik a minus b, right? The minus sign came down from the derivative, equals iq c. So I take the derivative and then plug in x equals 0. That was simple. But what is the problem? We have 3 unknowns and 2 equations. Where could the third equation come from? Well, obviously we know there's something that always exists in quantum mechanics.
World space.
We have to normalize, right? So if we want to normalize, technically, this is not true what I'm saying now, but if we want to normalize, we would have a third equation, and we could find all 3 coefficients. Why will this not work here? Because this is, by definition, a non-normalizable question. We started off with a free particle, starting with minus infinity. But in order for a wave function to be normalizable, it needs to go to 0 at infinity. So this question is by definition not normalizable. But the definition is okay, we can live with it. But we're talking about particles starting at minus infinity and then reaching plus infinity. So we cannot normalize this problem. So we're stuck with 2 equations. The thing is, we don't need to know all of them. We only have 2 unknowns. It looks like 3 unknowns, but we only have 2 unknowns. Notice that our unknowns only 2 unknowns. Our unknowns are the ratios. All we want to know is the ratio B over A and the ratio C over A. If we know our ratios, we're done. You don't need to know all the 3 explicitly. If we can find B as a function of A, and A only, so no C, and C as a function of A only, we'll just divide by A and we're done. Okay? So analyze your problem, you realize you only have 2 unknowns, which are the ratios. And because of this, it is very advisable, and this will save you a lot of trouble when you're solving your homework, and in general in life when you're solving this kind of problems. It is very advisable to divide your equations by A. And that way you can keep track of your equations. Look what happens. If you divide your equations by A, the first equation becomes 1 plus B over A equals C over A. And your second equation, I'll cancel the I as well, so you get K 1 plus B over A equals Q times C over A. Now since your unknowns are B over A and C over A, you have 2 equations, 2 unknowns. So remember this step, that you divide by A. If you don't do this, then it's possible to divide by them in the end, but it's easier to do that in the beginning, and then you know where you're going, you have a clear goal, instead of getting messed up with equations, especially in cases where the potential is a bit more complicated, like the previous example, when you had 5 coefficients, 5 unknowns, because you had 3 regions, and then you have 4 boundary conditions, 1 for x equals L and 1 for x equals 0. So then you don't get mixed up in the beginning, just divide by A before you start solving. That will save you a lot of trouble.
Is it a plus in the equation 2?
Sorry, it's a minus sign. Yeah, sorry, you're right. Yeah, absolutely, it's a minus sign. Okay, so 2 equations, 2 unknowns. This is simple, even I can solve this. We get B over A equals K minus Q divided by K plus Q, and we get C over A equals 2K divided by K plus Q. Right, it's about 2 steps. I'm just too lazy to do it on the whiteboard. But this is like 7th or 8th grade or something like that. So I'm sure you'll be fine with that. Which means we're almost done. What is left is to take the absolute value squared and plug in our k and q, which is the square root of this, right? So remember this, we'll need in a second. The refraction coefficient is k minus q divided by k plus q squared. So I'm going to plug in these values, and notice that all of the 2m over h bar squared will just cancel. So I'll just be left with e's and v naught. That's the root of e minus the root of e minus v naught divided by the root of e plus the root of e minus v naught squared. Okay? I'll take the square above and below, so I'll get e squared plus, I'll get e plus e minus v naught minus twice the root of e times e minus v naught. And here I'll get the same thing, just the plus sign. Now I will, this could be a final answer, right? But just so I can understand the answer, I'm going to divide the entire, and then divide above and below by e. I'm just multiplying by 1 in a fancy way. This way I can rewrite the equation. Notice this is 2e. So I'll get 2 minus v naught over e minus 2 root of 1 minus v naught over e. Is there a minus sign here? Should be a plus sign, right? Yeah, it should be a plus sign. I'm confused. And there's a 2 plus v naught over e plus twice the square root. Okay? It's just manipulating the... taking the square of this. So it's a minus b squared. I get a squared plus b squared, right? Should be a plus. Yeah, my notes are wrong.
No. It's still minus.
This is a minus. This? Oh, sorry, this is a minus. Yeah. Oh, stupid me. Yeah, it's this thing here. Okay, my notes are right. Take it back. Go notes. Okay, and we can do the same trick for t, the transmission coefficient. It's just this thing, absolute value squared. We'll plug in k and q. We'll divide above and below by 1 over e to exactly the same procedure. We'll get 4 times, the 4 of course is the 2 squared. So we get 4 times 1 minus v naught over e divided by the same denominator. And you can check that indeed the sum of this and this equals 1, because this 4 will go with this 2 and make a plus sign, and that's the same thing in the numerator and the denominator, you just get 1. Look at it for a minute at home, I'm sure you'll see it right away. So get, obviously, r plus t equals 1. Always when you finish solving this, check. Always. And if you hadn't done this, k divided by q divided by k, which I have erased. Sorry, here. If you hadn't done this, I already did it without telling you. So I plugged in this and then did q divided by k. Had you not done that, then you would not get r plus t equals 1. That would be like a red light. Watch out, you're doing something wrong. This is very important. Don't forget it. Questions?
Why can we use the t plus r equals 1 equation as a third equation to find the coefficients.
You will just find only R and then do 1 minus this and get this?
No, we said in the beginning that because we have 3 coefficients, A, B, and C,
Right.
and only 2 equations from the continuity of the wave function.
Right. I want to use R plus T equals 1. What the hell?
Right.
Just leave it this way.
Yeah, I knew that was going to go wrong. The day they built this is what's going to happen. It was so obvious. You want to use R plus, that's interesting. Probably could, because that's sort of a normalizable, normalizing condition, right? I haven't thought about this again. It's an interesting idea. Try and tell me what happened. Try and tell me what happened. It seems to me it'll work if you would be interested in right? If you're interested in knowing A, B, and C explicitly, I guess you could do that. It seems to me it will work. I can't guarantee you if I've tried it, but it seems to me that it'll work. On the other hand, why would you do it? I mean, it's nice to find the coefficients, but you don't need them. That's not what we're looking for, right? Because you also have no way of measuring your A or B or C individually. The only thing you can measure by experiment is this ratio. How many particles came through of the million we sent up, how many went back. So you wouldn't have a way of comparing to experiment anyway, so I wouldn't see why you want to do it in the first place. But if you want to do it as a mathematical exercise, I guess you could. There was another question?
Somebody there was a K and Q that in the T we said it was K divided by K plus Q.
Yeah, this thing.
Should not that K squared divided by K plus Q. That's confusing. I think it should be 2Q divided by K plus Q. But it was what?
You're talking about the ratio C over A?
Yeah.
No, that's 2K. I just go through the equations. It's 2K over there.
But if you all keep no wait.
Yeah, I jumped over 2 lines there. I'm sure if you take a minute and fill in, I'm sure you'll see it. What do you do when you finish? Right? So we finished here. We found R. We found T. We've checked that indeed R plus T equals 1. So we understand that our solution makes sense. It's actually a real physical solution. What you should do next is check limiting cases. Check limiting cases. What do we mean limiting cases? Check what happens for really large energies. Check what happens for really small energies. And see if you can learn some intuition, something intuitive about the physics going on here. So for example, you can look at the limit where E is much larger than V0. So we have a step potential barrier, but we have a very high energy. So classically speaking, a very high velocity. Particles are coming in with a very high velocity, very high energy. Like we said, the energy is just a kinetic term, so it's pretty much velocity. So let's see what happens to R and T in this limit. So this limit is the same as taking V naught over E to 0. That's the reason I wrote it in this form, because it'll be easier to look at this limit now. So in this limit, we get T equals to 1 and R equals to 0. So if I take V goes to 0 in this equation for R, then everything goes besides the 2. What am I doing? Sorry, you get 2 minus 2 upstairs and 2 plus 2 downstairs. But 2 minus 2 upstairs is 0, right, because this stays. So you get 0 for R, and for T, you get a 4 upstairs and a 2 plus 2 downstairs, which is also 4, so you get 1. Now why does this make sense? We're talking in this case about a potential barrier and a very large energy. So the energy is so high, the particle hardly sees the potential, it just flies past. is too energetic to be reflected. We see that in this case, our classical intuition is correct. So for very high energies, the classical solution is correct. But as soon as the energy is somewhat comparable to V naught, you get these coefficients. The other one we can look at is when the energy, when the energy is equal to V naught. We cannot look at the energy much smaller than V0 because by definition we solve the question where E is larger than V naught. So we can't look at a limit where the condition isn't satisfied. But we can look at what happens when E equals V naught. So where this V naught over E is equal to 1. In this case, we'll get T equals to 0 and R equals to 1. So exactly the opposite. And I'll leave it to you and the homework to understand this. And if you do not, then come and ask me. But you'll have something to think about at home. Questions? Did I confuse you? Think about it. It's a nice thing to think about. At home you'll first go through this solution again. You'll solve for E larger than larger than V naught. And I want you to go over it again, although I just did it, so you understand all the steps. You will then solve the opposite. And maybe then it will be easier to understand what happens at the limit after you've done these two. So that's why I'm not explaining to you now, because it'll be hard to explain to you before you've seen this case. So in your homework, do this again properly. Do not tell me we did it, so this is the solution. Do it properly. On purpose, I'm giving it to you again, so I want you to understand it. Then you'll solve this case, and then it'll be much easier to understand this limit. Okay, so we have 20 more minutes, and we are going to study the last example, second example. We're going to solve the delta barrier. So the potential equals to beta times delta x. So it looks something like this. Drawings of delta functions are always wrong because it cannot draw a delta function. It's only defined within an integral, but this one can think about it. Some really high and narrow peak. Of course, the initial conditions are exactly the same. The particle is starting all the way over there and coming in this direction with some definite momentum, some definite energy. And we are interested in finding the reflection and transmission coefficient of this problem. So find R and T. So again, we have to split up space. And the way we split up space is we look at the regions where x is different from 0. For x different than 0, the Hamiltonian is just the regular free particle Hamiltonian. There's no potential, because this thing is 0 for everywhere where the delta is not equal, where x is not equal to 0. So our regions are x smaller than 0 and x larger than 0. So in both regions, we get the same Schrodinger equation. And the solution of these equations is also simple. Should I risk it, or is this not going to work? No? Okay. Since I'm teaching quantum mechanics, I'm fine with taking the chance that it might not happen this time. It proves that you're still studying classically because you think it's going to happen again. the wave function, right, I solved this equation. It's exactly the same solution on both sides. I'm defining, of course, as always, defining k squared equals 2me over h bar squared. So the solution will be a e to the ikx plus b e to the minus ikx, incident and reflected. And on the other side, e to the I, c times e to the ikx, and no minus because there's no way it'll be reflected again. We talked about this. So this is for x smaller than 0, and this is for positive x. You can calculate your coefficients, your probability currents. You will see that they are just the regular coefficients with k, so there are no subtleties here. You will just find that r is b over a squared and t is c over a squared, because there's the same k on both sides. So this q over k business that we had earlier does not appear here. So all we want to find are the ratios, two unknowns, two ratios. For this, we need to use two boundary conditions. The first one is the continuity of psi. And the second one, I'm going to prove this to you, is the discontinuity, means not continuous, of the derivative. And this is a special feature of the delta function. The delta function causes the derivative to be discontinuous. So the limit from the left and the limit from the right, as x goes to 0, are not the same for psi prime.
How do you know it?
I'll prove it to you in a second, because I'm amazing and everything. From here we get a plus b equals c. That's just continuity. That's obvious. And as I told you, we divide by a. That's our important step. So that's our first equation. Now let me prove the discontinuity. And we'll go over this again as well. This is a very important step, very important thing to know. I'll start off with the Schrödinger equation. In the entire space. So I'll write it between minus infinity and plus infinity. So you have the potential term, the kinetic term, psi double prime, then there's a potential term, and that is equal to the energy times psi of x. Schrödinger equation, simple. Now I'm going to integrate from minus epsilon to plus epsilon, and then take the limit where epsilon goes to 0. Watch this. This is really fancy. I'm going to integrate dx, integral dx, and integral dx from minus epsilon to plus epsilon. The reason I would think of doing this in the first place is because I have a delta. The delta, I don't know what to do with it unless it's inside an integral. I have no idea there's no meaning to it, no mathematical at least meaning. I can think of, keep some physical intuition and draw pictures of diverging functions, but I cannot give mathematical meaning without integral. But now that I've done the integral, I can solve this. What is this?
Psi 0.
It's just the wave function at x equals 0. No matter how close epsilon gets to 0, this is true. Because 0 will always be between minus and plus epsilon as long as epsilon isn't equal to 0. As long as it's just, taking the limit and converging to 0. Now, this part, let's take it over here. What is the integral of the second derivative?
The first derivative.
The first derivative. Simple, right? And then I have to plug in.
At the point 0.
Let's put in epsilon for the moment, but yeah, to put in the upper and lower boundaries of the integral. So I get psi prime up to the constant here. That's psi prime at x equals plus epsilon minus psi prime at x equals minus epsilon. Is that clear? Nothing difficult about that. You take the derivative and then integrate, you're back where you started. Now what is this? Taking the integral over psi. Remember, psi is a continuous function. So I'm integrating a continuous function. I get some other function. And then I plug in the limit, the borders, and take the limit where the borders are equal to each other. Now the integral of a continuous function is continuous. Right? So if I take the continuous function at some point minus a continuous function at that same point, I always get 0. Is that clear? So it looks a little messy. Let me write it down again. What we got. So the first term is minus h bar squared over 2m psi prime. And let's take the limit to 0, right? Where epsilon goes to 0, so this is psi prime at 0 plus when we come from the positive side, minus psi prime at 0 minus when we come to 0 from the negative side, left. And then we have plus beta times psi at 0, and this equals to the right-hand side, which, as we said, vanishes. I'll now move this to the other side and multiply by this stuff. I'll put the minus into here. So what I'll get, after I shift this stuff around, is d psi to dx at 0 minus d psi dx at 0 plus equals to 2m beta over h bar squared times psi at 0. I've proven to you it's continuous. If I take the limit from the left side and from the right side, they do not cancel. There's some number, some constant. So the derivative of the wave function is not continuous.
But maybe the psi of 0 is 0.
Well, if that is the case, then yeah.
Because the potential is infinite, so of course it's 0.
Right. If psi, no.
The psi doesn't
No.
have to be 0.
Well, let's take a look at it. Where's our wave function? We erased it. Remember our wave function? So our wave function, right? So what is psi of 0? It's a plus b, or c, which are equal to each other, by the way. That's the first
But now I'm
condition.
thinking in the potential. The potential is infinite, and in the last class we
So
said
what?
that if the potential is infinite,
Over a finite space. The width of the potential is 0. It has no width. What you're saying is correct if there's actually a certain amount of space in which the potential is infinite. Here's not the case. Otherwise, this whole question would be stupid, right? It's not going to pass, right? No, you can tunnel through a delta function. Particle can tunnel through a delta function, and the wave function at x equals 0 is non-zero. Here it is. So I'll use this equation, this condition of this boundary condition. I'll take the derivative, I'll plug it in, I'll plug in psi at 0, which is either a plus b or c. Same thing. So, do this. So, derivative here is just ikc. So we get ikc minus ika plus ikb equals 2m beta over h plus squared c. I'll divide the entire equation by a. Right? That's the next step. You always do that right away, so you don't get confused and we don't work forever. So I'll divide the entire equation by a. I'll get ikc over a minus ik plus ikb over a equals 2m beta over h plus squared c divided by a. So we got two equations and two unknowns. Okay, questions about this? So the subtlety of this problem is these two lines. The discontinuity. It's a delta function. Besides that, it's exactly equivalent to all other scattering problems. Right? You find the currents, you find the wave function, you find the currents, you find the ratios, you plug them in, you're done. So it's exactly the same idea as all the other scattering problems. The only difference is the second boundary condition. So from here we solve for the equations, we solve for the ratios, plug them into the coefficients. After a couple of lines of algebra, we'll arrive at these two expressions. Also, this question is given the homework, and again, I would like you to go over it properly. I'm not just saying we did it in class. I won't accept that kind of answer. I want you to go over it, and of course, if you get stuck, go look at what we did. That's how you learn. So I'm doing this on purpose. You solve the questions again. If I would expect that a good student goes home after the lesson and then before he starts homework goes over the lecture and then starts solving homework. But I know no one does that, so I'm giving you the tutorial in the homework, so I'm forcing you to go over it. Okay, so if you answer, we did it in class, and this is the answer, I will not accept that answer. I want you to actually go through it. I want to see how you do it. Obviously, you can't only score 100 on that kind of question because you know the answer already. So take it as a chance to get a good score and to understand what's going on. So in the last couple of minutes, we have like 2 of them left. First of all, you see that r plus t equals 1. We always check that. I want to look at limiting cases. As I said, this is something we always do in the end. In order to train our physical intuition. So in the limit where beta goes to 0, So this is the case where the potential sort of disappears, right? Because the potential is beta times delta of x, right? So when beta goes to 0, if you look at our coefficients, you will see that t goes to 1 and r goes to 0. So if there is no potential, everything passes. That makes sense, right? If we look at the opposite limit, where beta goes to infinity, for some value of energy, that's the opposite, right? Where the potential becomes really, really high. That's what you were talking about, right? What happens in that case? You get t equals 0 and r equals infinity. E equals 1, sorry. R equals 1. So the potential comes impenetrable. You say that word. Can't penetrate the.
That was the right word.
Not penetratable. Wow. Okay? You can pass. What we can also do, like these were cases where we vary the potential, but for some value of energy. We didn't look at what happens to the energy. So what you can do, you can look at limiting cases for E. But this was for beta, here we're looking at cases for E. In order to do this, we have to plug in the relation between K and E, because there's no E in the equation, so I have to plug in that E equals h bar K squared over 2m, or in other words, that h bar to the fourth K squared equals 2h bar squared me. So everywhere we have an h bar to the fourth K squared, here, here, and here. We plug in this, we find that t equals 2h bar squared E divided by 2h bar squared E plus m beta squared, and we find that r equals m beta squared 2h bar squared E plus m beta squared. So now I'll hold B constant and take limiting cases for E. So if E goes to 0,
Is it not?
excuse me? If E goes to 0, so the velocity, the momentum of the particle, the energy particle is very, very low, it cannot pass the potential. It will always fly back. Potential is too strong. And in the opposite case, where the energy is very, very high, now we get the opposite. That t equals 1 and r equals 0, so it will fly across the potential as if it weren't there. So all these limiting cases make a lot of sense. And that's why it's always a good idea that when after you've finished your calculations, check, first of all, is it normalized? That's the first indication whether you went wrong somewhere or not. Of course, you must check your units. What are the units of T and R? The probability, dimensionless, it's probability. So that's of course the first way to check. Make sure that they're dimensionless. Then make sure that the sum equals to 1. And then go look at limiting cases. Be imaginative. Think about large energies, small energies, high potentials, low potentials. Those are in general the cases you can look at. You could also look at the case where the energy is equal to the potential height. That's also sometimes very interesting to look at. But these limits always give you some intuition. And they usually make sense, classically speaking as well. So this is a way to check your answers without doing a lot of work. Questions? Okay, so see you next week. Thank you very much.